morning, everyone. Welcome to the SpaceLab conference. My name is Liliang Wang. As you can see, both Professor Lin, Zhenzhou Lin, and myself are working for the Mechanical Engineering Department of Imperial College. And our research group is called Metal Forming and Materials Modeling. Our mission is to develop novel metal forming technologies and advanced material models. Our research outputs are mainly applied to the aerospace industry and the automotive industry. As you can see here, the China Academy of Launch Vehicle Technology, it is the biggest Chinese launch vehicle designer and manufacturer. We have a long-term partnership between each other for over 10 years already. Currently, in CAUT, which is the short name of China Academy of Launch Vehicle Technology, has a series of launch vehicle. It's called Long March series. It has 10 different models, and most of the products are being used for commercial use and the civil applications. As you probably know that, the Chinese government has recently started a big plan to explore the moon, which means CAUT has the mission to build extra-large launch vehicles. Currently, at the moment, CAUT, the biggest rocket or the biggest launch vehicle of CAUT, has a diameter of 3.8 meters. For the future, if they want to build an extra-large launch vehicle, the diameter will be over 8.5 meters. So you can imagine, from manufacturing point of view, there will be some difficulties or some issues. So that's why they asked us if we can help. So that's why we set up a long-term relationship. In the aerospace industry, lightweighting is very important, because if we want to transfer 1 kilogram of weight into the space, we need a cost of about 17,000 to 27,000 US dollars, which is very expensive. From economic point of view, lightweight manufacturing technologies will be critical for the aerospace industry. Over the last 10 years, we have been working on different projects with CAUT. Currently, over 50% of the components, structural components made by CAUT were made from aluminum alloys. And the requirement of these structural components are lightweight, complex shape, and high strength. We used to develop advanced and novel manufacturing technology called creep edge forming technology for them. And now it's being used to make the skin panels of the launch vehicle. However, this technology is only using a small deformation, which is elastic deformation, to make the part into a certain simple shaped component. However, if they want complicated shaped components to be manufactured, we have to offer them something different. We developed a novel forming technology called HFQ forming. So what is HFQ forming? The basic principles are shown here. So at the very beginning, we put an aluminum blank into the furnace to heat up the material to the solution heat treatment temperature. And then we transfer the material quickly from the hot furnace to a piece of cold die. Normally, the cold die are water cooled. And then we form the components very quickly by using the cold die, and the formed components is held within the cold die for a certain period of time, which will normally take a few seconds. And afterwards, we will put the formed components into another furnace for artificial aging. By doing this, we can achieve the full strength of the material. This is a very novel forming technology to combine metal forming and heat treatment in one operation. Since we form the components at solution heat treatment temperature, so the ductility of the material is very high. then we can form the components with very complicated geometry. And since we're using quenching from the cold die, so supersaturated solid solution state will be obtained after forming. And after artificial aging, we can retain the full mechanical strength of this material. This technology was invented at Imperial 10 years ago. So over the last years, we have been studying this technology intensively. So we have been using this technology to form different alloys, including many different types of aluminum, high-strength aluminum alloys. This is a real component from Airbus. This component is called wing stiffener. Actually, it was made from CNC machining previously. They used a big block of material and used CNC machining to remove over 90% of the material away to make one component. So you can imagine the cost is very high. To make each one of these components will cost over $180. So Airbus came to us the other day and asked if we can use a piece of sheet metal to form the components directly. This will be much cheaper. So we tried the material. They used AA2024, which is a very high-strength aluminum alloy. We used conventional metal forming technology. As expected, it was failed. And then we developed our own tool and formed by using our HFQ forming technology. It was very successful. And we tried different materials as well, 682, 6111, 5000 series as well. They are all very successful. And in terms of the cost, if we take the tooling cost included as well, if we form the components by using the HFQ technology, the cost will be less than $10. So the cost saving is very obvious. We have another customer, the other day came to us and asking us if we can use 6000 series to form a very complicated shape, real components. And they provide us the die, and we tried by using their original material, which is in T6 condition. This is the maximum strength of this material. And we developed our own tool in our lab, and we formed by using HFQ technology very successfully again. So the part is very complicated in shape. At room temperature, we can't form the part at all. And the repeatability of this technology has been verified. This is very important. So we check the post-form strength of our technology. We can achieve the yield strength of over 300 megapascal, which is equivalent to the maximum strength of this material. This is very important for the customer because by using this kind of strength, they can save up to 50% if they compare to their original aluminum alloys component. This technology cannot be only used for aluminum alloys. It can be used for magnesium alloys as well. As we probably know that magnesium alloy probably is the lightest metal which can be used to manufacture structural components. However, it's very brittle at room temperature, so it's not possible to be formed. At Imperial, we have the latest model of Galibo, which is the most advanced material tester in the world. So we can simulate the complicated temperature evolution during the deformation process. Of course, we can simulate or reproduce the HFQ temperature evolution. We can see that, especially from at room temperature, the ductility of the material is very, very low, very, very poor. So it's not possible to form any shape by cold forming or traditional metal forming technologies. But if we look at this curve, which is the HFQ forming condition, the ductility has increased significantly. So we use this forming condition to form the part very successfully. All the previous results introduced by myself was realized in the lab scale. What if we apply this technology in the industrial production line? What will happen? Actually, a few years ago, we went to Sweden, APNT, and we have realized our technology in a real existing production line. This video shows a speed feeder took out the specimen from a furnace and put the specimen onto the die and formed very quickly and hold within the cold die for a few seconds, and the part was formed very successfully. They put a very nice logo here, APNT. And this is the production line, small-scale production line of APNT. The other day, Cloud came to see us. Since they knew about HFQ technology, they are very interested. But they asked us if we can offer them some other technology which can be used to form ultra-high-strength aluminum alloys, which is, for example, 7075. In addition, they ask us if we can reduce the cost of the forming technology so that they can save money. So we said, sure, we can. We offered them another technology, which is called fast hot stamping technology. This novel technology will be as cheap as the cold stamping of aluminum alloy and as fast as cold stamping of aluminum alloy. So the basic principle is that we are working in this area, which is the metal forming area. And this graph shows the temperature evolution during the HFQ forming process. The x-axis is the time. The y-axis is the temperature. So the aluminum blanks are normally provided by the material producer by hot rolling. So you can see this is the temperature. At very high temperature, they roll the aluminum ingot into a sheet blank. If the material has a very poor ductility, a few annealing process will take place. After that, they will solution heat treat the material, and artificial aging will take place, and then we can purchase the material in T6 or in T4 condition. And then we conduct HFQ forming, and after HFQ forming, we will conduct the artificial aging. Then the components will be supplied to OEMs, for example, aerospace industry. That's the normal procedure. As you can see here, we have two solution heat treatment procedures, and we have two artificial aging procedures, which is a waste of money and also the time. That's because currently in the market we can only buy the material in T4 or T6 conditions. And recently we have convinced the material supplier to provide us the material in the ice-rolled condition. So they don't have to put heat treatment into their material production line. So we just use the material in the ice-rolled state for HFQ forming. And also here, we use some dedicated equipment to determine the key forming parameters of this new forming process. We determined the critical cooling rate, critical cooling temperature, and the critical soaking time. These are the three key forming parameters in this technology. By using this, we can realize that the artificial aging process will be totally removed from this technology. So we will save money. And the raw material cost will be very low because they don't need to do the solution heat treatment and artificial aging, etc. We realized this idea again at APNT. So this is their latest model of the furnace, which is multi-layer furnace, which can be controlled independently. So the hot blank was brought out by the speed feeder, put into the cold die, and formed very quickly. So the part can be formed very successfully. And here is the picture of me. We tried. By using the conventional cold forming technology, you can't even bend the material. So the material is so brittle at room temperature. but by using our technology, the part was formed very successfully. And there are some primary benefits for the aerospace industry. For example, we can meet their requirement for the lightweight, complex shape, and high strength. And also, for this technology, we have some secondary benefits, including the low cost, high productivity, no natural aging effect at room temperature, and the secondary feasibility for the fabrications. And immediately after fast hot stamping, we can see this is the tensile strain stress curve. So the part is very ductile. The remaining ductility is about 20%, which means you can conduct something like hemming, bending, or self-piercing. That's possible. And after aging process, we can achieve nearly 500 megapascal in the component. So it's very strong, and we don't need extra artificial aging process. This is a new forming technology. So for the designers, it's very difficult because previously they have established the knowledge to design the components. They know exactly how much deformation can be achieved in the conventional forming technology. But when we introduce the new forming technology, they get confused. They don't know how to design the components. They don't know how complicated they can achieve by using this technology. So they need knowledge from us. And we developed advanced material models to capture the flow stress evolution at different temperatures and different strain rates. The material models are very accurate, and also we developed our own forming limit prediction model to predict the failure of the component. And this simulation results shows a very complicated aluminum component formed by using our technology. This is a door inner. And also by using our model, we can predict the failure. So if you get an idea to design the component, we can tell you how much deformation can be achieved by our technology. Okay, I'll stop here. Thank you very much.